Okay, yeah. All right, so I'm going to work on my tablet. And at the end of the last class, I talked about the work of expansion against a constant pressure. And we came up with an equation for that. From last time. And we got, well, minus P2 times V2 minus V1. But then if you use the ideal gas law and you put in for that, this is what it looks like if you don't restrict the temperature to being constant. So this is, you know, the temperature can change because you see I have two different temperatures here. But if T1 is equal to T2, so it's an isothermal process, the temperature doesn't change, then we can factor out the nRT, right? T equals T1 is T2. So this is where we ended last time. And then we had P2 over P2 minus P2 over P1, or minus nRT 1 minus P2 over P1. So this is for a constant pressure expansion, isothermal. A lot of times I would call it an isothermal expansion at a constant pressure. That's sort of more along the lines of what I would call it usually. And you could see that if P2, so I'm just reviewing from last time, if P2 is less than P1, which is true of an expansion, right? Then this thing is less than 1, and then the work is negative. So work is done when the gas expands, and so it's negative. It's done. We actually, in full language, to put it correctly, actually, we would say work is done by the system when it expands. And you would say work is done on the system when it contracts. So that would be the case if P2 is greater than P1. Then the surroundings would be doing work on the system. In a contraction, in a compression. Okay, and in that case, of course, the work would be positive because P2 would be greater than P1, but and corresponding to V2 being less than V1. Okay, just to get the language straight on that. All right, so I have this handout, which maybe you took a look at, because I did tell you about it today, but you don't have to have taken a look at it. It's just a little exercise I'd like you to look at and do. So if you wouldn't mind to do it, just work on it. It shouldn't take very long. Just take a few minutes, read the thing, and do the first couple of parts. So Benjamin, we're just working on this problem now, okay? Because you just came in.
Oh, okay.
So I'm
Thank
just
you.
giving you a few minutes to work. I'll read it and work on it. I didn't send it to you by email,
Okay.
but it's posted on Blackboard. It says, well, it's among those slides. I referred to those slides that I posted on Blackboard.
Oh, okay.
If you go on Blackboard, it says what we're going to be doing in class today. You can look there and you can find it.
All right.
Oh, I think I forgot this section on what is the work. Oh yeah, what is the work? I don't know if everyone can read what they need here. I wouldn't mind if you went on and did this part where you calculate the work. Can you read that? Yeah, okay. Would you like to talk about this part? Is everyone understanding that part? I'm just going to wait a few more minutes. Oops. I think maybe I'm ready to talk about this problem a little bit. You made some progress on it, right? Let me talk about the first part. So what is it asking you to do here? So we have a vacuum in here. That's why these pins have to be in here, because obviously there's a pressure pointing in this direction, right? But there is no pressure opposing it, right? Because there's no gas in there. Make sense? Yeah. okay, it tells you what the gas pressure is. That's the 10 atmospheres here. And it tells you the volume. Well, the volume is V1. The volume of the whole container is V2. Temperature is 305. The pins are removed, okay? So there is no arrow represent the internal pressure. There is no internal pressure, so there's no arrow there. So dW is defined as, somebody give me the definition.
Isn't that the volume that the
Just the definition of the work, not the answer, just the definition that we learned about last time. It's minus P external times its volume, right? So now I have to ask you, you know, what is dW equal to in this expansion? What is P external?
10?
No, that's P gas. That's the
It's zero.
inside.
It's 0.
Yeah, it's 0. So P external is equal to 0. So dW is equal to 0. So the gas doesn't actually do any work in this situation because it's pushing against 0 pressure. And of course, we assume that very idealized wall has no mass and things like that, but there's no external pressure here, so there is no work done, okay? So the work of this expansion is 0. And why have I left so little space to do this problem is because there's nothing to do, right? It's just 0. Yeah, so basically to get the work, it would be dW would be minus, that would be the integral of P external dV, but this is equal to 0, so we're done, 0. Okay. Sorry, this would be work, not dW. Anyway, okay, so now we have a different situation, right? We have a situation where we have an ideal gas, and you've got the 2 pins again, and a mass is placed, and the mass is exerting a pressure that's 2.5 atmospheres. And the gas has a pressure of 10 atmospheres. So the external pressure has an arrow that's quite a bit smaller if the arrow reflects the strength of the pressure, right? There's a much smaller pressure from the outside than from the inside, okay? So these arrows should look something like this, where the top one is smaller than the bottom one. And so now this thing expands. So V1, it should be simply nRT over P1. Did anybody come up with that? 1 mole? Did anybody get that answer? It's kind of a nice symmetrical answer. It actually comes out to 2.50 liters. Okay, that's the initial volume. And the final volume, so now it's the same on top. And P2 is 2.5. So this comes out to 10 liters, or 3 sig figs really, 10.0. Okay. So that's what the final volume is. So the work, the integral of dW, well, that's the integral of minus P external dV. We went through this last class. P external, here, it's constant, right? We have this mass sitting on top, and that mass does not change. Right, so P external is constant. So we can take it out of the integral. And the integral of dV is just V2 minus V1. Okay, and we just calculated V2 and V1. So the external pressure, that's the 2.50. This is the 10 that we started with. Yeah. Exerts a pressure of 2.5, so that's 2.50 atmospheres times 10.0 minus 2.50. Okay, so did anybody get up to this point? Probably not, but anyway, it's simple to do this calculation, and you get negative 18.75, but there's only 3 sig figs, so I'll underline the 7. And the unit of this thing is a liter atmosphere. Liter atmospheres, all right? So work has, this is an energy unit, right? Work has units of energy. You could have joules of work, right? So a liter atmosphere is a very weird energy unit. So I sort of skipped over this question. When does the expansion stop? It stops when the gas pressure is equal to the external pressure. So it stops when the arrows become equal up. So it stops when the inner arrow becomes as small as the outer arrow. We call that mechanical equilibrium. Because as the expansion happens, P gas drops as it's expanding. When it equals P external, the expansion stops. And the final pressure is the external pressure. Okay. So we did 18.75 liter atmospheres of work. Okay, and it's negative because the system is doing it. So now it says that you can convert this strange unit into joules by using the fact that the gas constant has these different units. So what you can do is you could say, okay, negative 18.75 liter atmospheres, but I know that 8.314 joules per mole Kelvin equals 0.08206 liter atmospheres. Leave enough room here. Per mole Kelvin, and moles Kelvins cancels out. And that's the joules per liter atmosphere, which if you wanted to actually, you know, figure out that number, it's about 101.3. But in any case, this comes out when you do this to negative 1.90. Hold on a minute. Oh, it's the same old, you know. I don't even know what's going on here. How come there's 2 different things? This is what happened when this computer heats up, so I have to do what I always do. Stop the share, close the thing down. I just love online teaching. Oh, you know, I think I forgot. Did I record? I did, right? Shoot, I think I did. I'll be back. I guess I can stop the recording for a few minutes. I'll pause it. All right. Oops. Gotta love it. Well, I'm back for I don't know how long because the thing isn't moving again. Oh, it's muted. Well, that's right. No, it's not. All right. Well, okay. Did anybody manage to do this next part without me? So this comes out to, when you multiply this out, it comes out to minus 1.90 times 10 to the third joules, okay? And if you use this equation here, which I just gave you a little while ago, you could see you get the same answer, 1 mole. And now here for R, if you use the number in joules, and then you have sorry, I forgot the temperature, 305, 1 minus P2, which is 2.50 over 10, and it comes out to the same thing. Okay, so there's many ways to handle some of these problems. All right, so that is an example. You've done your first, work calculation. All right. Yeah. So that's how you calculate the work of expansion. That's an isothermal expansion against a constant pressure. Okay, so I'm going to do another special case now, which is called the reversible expansion. So this is a very important kind of expansion that it's sort of like the opposite thing as a constant pressure expansion. And so here's how it goes. In a reversible expansion, I always tell those students to think about a pile of sand, okay? And so instead of having a block on top like we did before, where the block doesn't change its mass, it's just always that constant pressure, we have a pile of sand, and the sand exerts a pressure. We call that P external, just to show here with the red arrow pointing down. But in this case, what happens is that the system and the surroundings always have the same pressure. So you might ask, how is it that you can have an expansion where the external and internal pressures are the same, which means you're always in mechanical equilibrium. Okay, so we always have the same size arrows here. And you don't need to have a pin. Remember in the other example, the internal pressure was so much higher that we had to keep the top down or it would automatically just go up. So the question is, how on earth can the gas expand? With these restrictions on the pressures. Okay, so I'm going to show you, and this is why we have to think sand. Okay, so let's follow the procedure here, okay? So I take 1 grain of sand away, just 1 grain. What happens? Okay, so the external pressure drops by a tiny bit. In a real reversible process, that's an infinitesimal. That's a dP, okay? So we take off that's why I'd say to think sand, because each grain of sand itself exerts such a tiny pressure. So you remove a grain of sand, the external pressure drops by that pressure. Now, there's an ever so slight difference between the external and the internal pressure, an infinitesimal difference. So now P gas is just slightly larger than P external. And so you get a small expansion. The system expands by a tiny bit. And when it does, its pressure goes down because it's expanded, okay? And its volume has increased, the temperature, the pressure decreases. And we repeat this process, removing other grains of sand. We do this one grain of sand at a time, and each time the pressure changes by a tiny bit. Each time the gas expands a tiny bit, and its pressure becomes equal to the external pressure. And if these little tiny bits are infinitesimals, that's when we have something that we call a reversible expansion. It's a very important type of process in physical chemistry. What happens is that the external pressure and the gas pressure are equal at all times. Within an infinitesimal is equal, okay? But of course, it has to be that infinitesimal. You wouldn't have that expansion, okay? And yet the gas has expanded. So this is very controlled. It's also very unnatural, okay? So here are what the initial and final situations look like, okay? So the gas starts at P1, just like it did before, and it ends at P2, just like at the constant pressure case. So the gas pressure changes the same way exactly. It's the external pressure that's different, because the external pressure in the constant pressure case was constant, and now it goes from being a giant arrow to being a little arrow, right? Becomes equal to the gas pressure. Starts out equal to the, well, it's always equal to the gas pressure. So notice you have big arrows on both here, you have little arrows on both here, okay? So we're going to compare these side by side in a minute, but first I want to talk about why it's called reversible. So let's do that, and then I'm going to put these side by side. Well, after I do the work, then I'm going to compare the two situations sort of side by side, and we'll point out what's going on with those pressures if you didn't catch it the first time. So why is it called reversible? Well, reversible is something that can be easily reversed, and that's exactly why it's called reversible. So because the process can be easily reversed. So how do you reverse it? Well, instead of removing a sand grain, you add a sand grain, okay? So you add instead of remove a sand grain, okay? So if you add a sand grain, now the external pressure becomes slightly greater than the gas pressure, okay? And so now we'll have a tiny bit of compression will happen until P gas is equal to P external. But it's just a tiny, small, tiny bit of compression. And that will slightly increase the gas pressure to equal the external pressure. Wait, let me think about it. Did I say that right? Yes, okay. So here's the thing, it's a reversible process. Can be reversed by an infinitesimal change in the opposite direction, okay? Oh, I should maybe reversed by an infinitesimal change in the opposite direction. So let's think back to the constant pressure expansion, where we had something that looks like this. You know, you have a larger pressure on the outside and a small pressure on the inside. And you had these pins here, but then, you know, someone comes along and takes those pins out, and this thing goes whoosh, right? There's a large pressure imbalance between the inside and the outside. Now, if I took a sand grain, here's my sand grain, and I dropped it on top of that piston while it's moving, while it's expanding, is anything going to change about the direction of that expansion? No. This is a more directed change. It will not reverse by changing the external pressure by an infinitesimal. You know, I'd have to drop a rock on this thing for it to stop, you know, something much heavier. Okay, so a constant pressure expansion, we call it irreversible. Because you can't change it by changing the pressure by an infinitesimal. But there are other words for this, okay? We say that it is spontaneous. It has a particular direction and it's not going to change from that direction. So they're really very different processes, and they have different amounts of work. So we've already calculated the work of a constant pressure expansion. So now I'm going to calculate the reversible work. So that's the next thing. All right. So here's the diagram of the initial and the final state. Initially, I have a pressure P1, a volume V1. At the ends, I have a pressure P2 and a volume V2. So if you look at this state of the gas initially and at the end, it's changed exactly in the same way as the constant pressure expansion. But let's calculate the work because it's a different story entirely. Okay, so we're going to use our definition of dW as minus P external dV. Okay, you have the same definition, but now P external is not constant. You can see the arrow goes from being equal to the big pressure of the gas at the beginning to being equal to the little pressure of the gas at the end. Okay, so those they're not the same. So the work is going to be the integral of this. But now we have to think about P external. Okay, so what do we know about it, right? We know that at every point in the expansion, it basically equals the gas pressure, right? We're taking the sand off a grain at a time, and the pressure of the gas is never more than an infinitesimal different from the pressure externally. So they're equal, right? P external is equal to P gas. The pressures never differ by more than an infinitesimal. So I'm just saying a sand grain is an infinitesimal. Okay, so if that's the case, then this P external here is equal to the pressure of the gas, which I'm just going to call P, right? So W is minus the integral of P dV, but P is not constant anymore because as that gas expands, with every little teeny bit of expansion, that pressure is going down. What is that pressure equal to? Well, it's equal to nRT over V. Whenever the volume goes down a little, the pressure, sorry, whenever the volume goes up a little, the pressure goes down a little. Okay, so I can say W is minus nRT over V dV. Okay, and now if I say that T is constant, so I'm calling this an isothermal. This is an isothermal reversible expansion. So before we had an isothermal expansion against a constant pressure. Now we have an isothermal reversible expansion. So if T is constant, I can take all of these guys out of the integral, minus nRT, the integral of dV over V. And now I get to the important revelation of physical chemistry, okay? This is the integral we do 90% of the time, is d something over something. So you have to know what that integral is. So it's not like Calc 2 where we integrate these crazy things. It's not like that at all. Integral of dV over V is the natural log. And we would have limits on it. It would be the natural log of V2 minus the natural log of V1. Okay, because the integral of dx over x is natural log of x. But that's not how we normally express it. We will express this as n minus nRT log of V2 over V1. And that's actually not the way we express it most of the time. Because usually in problems of this type, you're not given the initial and the final volumes. You're usually given initial and final pressures, not volumes. So that's fine because we know that at constant temperature, P1V1 is P2V2. So that says that V2 over V1 is P1 over P2. So that's Boyle's law. So we end up with minus nRT log P1. Notice the P1 is on top. Okay. And again, let's look at this. So if V2 is greater than V1, that's an expansion, then P1 is less than P2, right? And then this is the natural log of something less than, wait a minute. Sorry, V2 is greater than 1. I have that backwards. If V2 is greater than 1, then P2 is less than P1. And so this is a number greater than 1. And so this is positive. And so this makes the work negative. Of course, if we have a compression, then P1 is less than P2. And this is less than 1. Okay. So it's, everything seems to work out with this formula. So I just want to go back and show you the initial and final states again, and just point out the differences here. between the reversible and the constant pressure situations, okay? So what's different about these diagrams? It's really only one arrow that's different. You know, here you end up with the same pressures here, 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 and here, okay? The only difference is that this arrow, okay? And that makes all the difference, right? Because the external pressure in the reversible expansion is always equal to the gas pressure. It starts out just as big as the gas pressure here. So these are always the same. So what that means is that gas in the reversible expansion, that gas is always pushing against a greater pressure than it is here. Here, look at that arrow, that external pressure that's pushing against is smaller. The only time it's pushing against the same pressure is at the end. Okay, so I guess I would say that for the reversible expansion, the gas is always pushing harder. Always pushing against a greater external pressure than in the constant pressure expansion case. Okay, so that means that the gas is going to do more work. So here, at all points, P external equals P gas. And that gas can't push any harder than its own pressure. And that's what it's doing in this case. Gas cannot push any harder than this. It can't push harder than its own pressure. Or infinitesimally less. Okay, here, until it gets to the ends, here the gas pushes against a lower pressure. Let's see what else I want to say about this. So the reversible case is very gradual, very controlled. You have to have a little guy on top of the piston throwing off the sand grains, you know, that's not something you would see in a factory, for example, you know, nothing is going, you know, if you have a power plant, you're not going to have a reversible expansion as part of it. You have the system and the surroundings are always in mechanical equilibrium. Here, that's not the case. Here you have a directed change. P gas is always greater than P external until the end. You only have that mechanical equilibrium at the end. Now, I remember when I took a course in thermodynamics at Brown, I was in grad school. I had this teacher, he was from Belgium. He had this cute accent, you know. But honestly, I don't remember, you know, at that time, it was a couple of years since I'd been in college, at least, and taken thermodynamics. It'd been a bit, and I didn't remember a thing, you know. So I used to have lunch with the Greeks. The Greeks were very friendly, and I'd have lunch with them, and they would tell me how they figured out the difference between when he was saying reversible and when he was saying irreversible. Because with his accent, he would say reversible and he'd say irreversible. I mean, it almost sounded exactly the same. So how do you tell the difference? So they were funny. They would say, okay, whenever he's saying reversible, he moves his shoulders forward and back at the same. reversible, irreversible. So anyway, we all thought that was the key to figuring out what, because if you don't know what he's talking about, then you really don't have a chance to figure out what it really means. So if it wasn't for the Greeks, I'd still be shaking my head and trying to figure out what reversible and irreversible means. But they were laughing hysterically, and of course speaking Greek when I approached them at lunch. And I soon found out what they were talking about. It was very funny. Anyway, so what I want to do next is show you how you can visualize this work, okay? Because remember, this is an isothermal expansion. And we know what happens to, we know that in this expansion, the external pressure is following the gas pressure. We're keeping them within an infinitesimal of each other. And the gas pressure, as those grain of sand come off, what's happening to the volume? Well, the volume is following an isotherm, okay? So how does the pressure of a gas vary with V? It follows the isotherm. So that's what's happening to the pressure. We know exactly what's happening to the pressure. So how do we represent the work? Well, what is the work, right? It's the integral of the external pressure times the change in volume. But the external pressure is the same as the gas pressure. So what that means is it's all along here, these dots are representing the pressure, the external pressure for an isothermal expansion, because it's the same as the gas pressure. So that means in the integral, if I take my little dV here, right, that's my dV, and I multiply it by this value of the pressure, I get this little area. And then if I do it again, I get the next area, and I do it again. So if I add up all these pressures multiplied by the change in volume, what I end up getting is the area under this curve, right? So the area under the pressure volume isotherm from the initial to the final volume equals the reversible work. Something else I wanted to say about that. What was it? Oh, not exactly, right? Because this area is not negative, all right? It is actually the magnitude of the work, because the work is negative. So the magnitude of the work is equal to the area. Okay, so I'm just summing up all these little PDV things. That's what an integral is. It's an infinite sum. So that's what I have to say about that. Now, how do I represent the constant pressure expansion? Well, that's really even easier. So just to give it give some perspective, I'm going to put the PV isotherm here as well. So here's my initial pressure and volume. This is the gas pressure, the gas volume, and here's the final. But the gas pressure is not the same as the external pressure, except at the end, right here. And you can see that's where the isotherm hits this line. This is the constant pressure line right here, this red line. And P external, remember, that is the final pressure of the gas, because the gas stops expanding when the pressure inside and outside are equal. So P external equals P2, so this is P external. And remember that what you get here is minus P2, V2 minus V1, right? This is V2 minus V1 here. This is P2, and it's simply this area. It's a much smaller area, okay? Because this is the pressure that the gas is pushing against the entire time, okay? That's not the same as what's happening here, where this is the pressure and it's constantly changing over the course of that expansion. So when I ask you, why is the work for an isothermal reversible expansion more? You say, it's because the gas is pushing against a greater external pressure at every point except the last point in that expansion. And I gave you the other equation for this, but I don't see why. So this comes out to minus nRT 1 minus P2 over P1 when you put all the other stuff in. So if you look at these next to each other, there they are. You can see this illustrated again, really the same thing. So P external always equals P gas for the reversible case. It changes as the gas expands. That's not true in the constant pressure case. They're only equal at the end. At every point, the external pressure is less than the gas pressure for a constant pressure expansion. So the gas always pushes against a smaller pressure in the constant pressure case. The reversible expansion has a greater external pressure at all points. So it's pushing against a greater pressure. So more work is done in the reversible case. And not only that, but the reversible work is the most that that gas can do because it can't push any harder than against its own pressure. Okay, so I think I've beaten that enough. So now let's see. You could see that we have sort of shown by example this very important fact that work is path dependent. Now, what we have really is, you know, we started at the same initial state of the gas. We had P1, V1, and T. And we ended up at the same final state. But we did a different amount of work, reversibly and at constant pressure. And that's why I say that work is path dependent, because we started and ended in the same place as far as the gas was concerned, but we ended up doing a different amount of work. Okay, so, all right, work changed. Well, what about the internal energy? Does it depend on path? Okay, so we're going to take sort of a brief segue into chapter 3, and really we're not going to do much at all in this course from chapter 3, but one thing we do is we talk about the difference between the kind of function the work is and the kind of function internal energy is. They're very different, and you've heard this terminology before. The internal energy, unlike the work, is what we call a state function. Okay? The value of that internal energy depends only on where the system is right now and not how it got there. It depends on the current conditions. Not on how the system got there. So if you start at state 1 and you end up at state 2, and you know, using this term state should be like kind of okay with you, because I showed you, remember that 3D graph of the states of an ideal gas. So really the state of an ideal gas is really just, you know, what is its moles, temperature, pressure, and volume. And there's a relationship between those 4, so you really only need 3 of them. And if you say it's 1 mole, then you really need 2 to get the third. So that's what I mean by state. The state is defined by the pressure, volume, temperature, and the number of moles. So if you go from state 1 to state 2 with one path, and you go with another path, or you go with a third path, you always get the same delta U. Delta U is always the same. It's always whatever the internal energy is at state 2 minus whatever the internal energy is at state 1. It's always like that. But W is not like that, because we just saw an example where we had two different paths and we had two different values of the work. So work is not like that. Okay, but we have something very important, right? We have the first law. And the first law says that the change in internal energy is the sum of the heat and work contributions. So if W is path dependent and U is path independent, so this does not dependent on path, it's just U2 minus U1, then what does that say about Q? That also has to be path dependent. Otherwise, delta U wouldn't be the same. If you only have W that's path dependent and Q isn't, okay? So just to show, to talk a little bit about a sort of a garden variety, more familiar function. So a more familiar state function is like the gravitational potential energy. You know, if I define the zero of potential energy as my tabletop, right, then, and the height above that table, so that's the zero. So PE is mgh. H is the height above the tabletop. So what's the change in potential energy as you go from one height to another? It's going to be mgh2 minus mgh1. Right, this is PE2 minus PE1. And so that's just mg times the change in height. So if I take a book, you know, I have a book on the table, let's say. I don't have a book next to me, but if I took a book and I pick it up and put it down, pick it up and put it down, and pick it up, and I do that like 100 times, the potential energy of that file folder or that book on the table when I started and when I ended is exactly the same. So if delta H equals 0, delta PE equals 0, you know, you can lift a book up and down, you know, 100 times. The delta PE is 0 because you didn't change the height, but you did a lot of work. I could be all exhausted with my arms tired and everything, right? So that's the difference between work, you know, being path dependent and potential energy not being path dependent. So here's another thing that comes about in chapter 3. So you should read the first, what did I say? Let me see, what sections? Three 1 and 3 2. Talks about path dependent and path independence, stuff like that, and also some other things we'll get to about exact and inexact differentials. So here's something else that comes up in this section, and that is, here's the fact. Let's talk about it. Here it is. I'm going to write it down. For an ideal gas that is not undergoing a reaction or a phase change. And is held at constant temperature the change in the internal energy is equal to 0. All right. So why does this make sense? Anybody? What is the internal energy for an ideal gas? So normally it's the internal energy is the sum of all the translational, vibrational, rotational, kinetic energy. It's got attractions and repulsions. It's got chemical bonds. But an ideal gas, you know, just like here, there's one, like say monatomic ideal gas. It has just kinetic energy. And the kinetic energy, we know the average kinetic energy is 3/2 RT. So it depends on the temperature and on nothing else. It doesn't have any of those other things. So this is the internal energy. And remember, I told you earlier that I'm ignoring all these energies for when the temperature is absolute 0 that physicists care about, because I don't care about them. So U is 3/2 RT. And if the temperature is constant, then delta U is equal to 0. So if you have an ideal gas and it undergoes an expansion, okay, and it does work, but its delta U is equal to 0 because the temperature, sorry, an isothermal expansion. Since the delta T is equal to 0, it means that delta U is equal to 0. But if delta U is Q plus W is equal to 0, then how are these guys related? Right? Q is equal and opposite to W. So this means that when that gas expands isothermally and does work, in order to keep it at that temperature, you have to have a constant input of heat. Because remember, the work is negative, so the Q is positive. And they have to be equal in magnitude. Okay, so basically here you have your expansion. Work is done, okay? Heat has to go in. Same amount as the work that's done. You can think about it this way, that if that gas expanded and heat didn't go in, then the energy to do that work has to come from somewhere, and it would come from the internal energy of the system. Now that's what's going to happen when we have a different type of expansion. When we have, say, what we call an adiabatic. So first of all, I'll get to that in a minute. But let's say, so we have that this is the situation for an isothermal expansion. Heat in is the same amount. Okay. So if heat didn't go in, then the internal energy would have to drop because of the energy has to come from somewhere. That's the first law. And we use the first law, right, to get the fact that Q is minus W, right? So how can you keep the temperature? How to keep the temperature constant? You know, how could that physically be done? I'm going to draw some ridiculous pictures here, but let's say you had a big heat bath, right? You put your little piston in here, doing its little expansion. Okay, and you have this big heat bath held at a constant temperature. So, you know, if this thing expanded and cooled a little, instantly some heat would go in to restore it to the temperature of the environment. So that's one way to do it. More commonly, you might have a system where you basically had kind of flowing in heated water or something. And you wouldn't need this. I was silly putting that there. And then you would have it thermostated. So as soon, you could have a thermostat in here or a thermocouple measuring the temperature. And as soon as the temperature dropped, it would put some more heat in and it would keep the temperature constant. All right, so you definitely could think of how this could be done in real life. Yeah, but I wanted to say, okay, wait, hold on. So I wanted to get back to the idea of what if heat couldn't flow in? So in other words, what if you had your system that was somehow insulated? So no heat can flow. And if the system expands, in that case, what's going to happen? So if system expands, what's going to happen? Well, it's doing work, right? But no heat is coming in. So what's going to happen to the internal energy? What's going to change in internal energy? So delta U is Q plus W. If Q is 0, then delta U is going to equal W. And if the work is negative, then delta U is negative. So what's that gas? If it's an ideal gas, what's going to happen to it? Think about it. If no heat can come in, then that energy has to come from somewhere, right? It's going to come from the system's own internal energy. So what does the internal energy of the system, if it's just an ideal gas, depend on?
Yeah.
What? I heard something sounded promising.
Are you asking if the internal energy is going to go up or down?
It's going to go down, right? Delta U is negative. What happens to the temperature? Remember,
Wouldn't the temperature go down?
the temperature has to go down. So, if you can't get that heat coming in, it's not going to be able to be isothermal. Now, this type of expansion is called an adiabatic expansion. And that's when Q is equal to 0, when we have this insulation here. Okay? It's a different topic now. That's something we're going to cover in a little while. But what I kind of want to tell you here is that in PChem, you'll notice we always handle idealized situations. Okay? So you'll notice this over and over again. Idealized situations. Okay, so what we've been talking about today is an isothermal expansion. We did it reversibly and at constant pressure. But all of these things can be in between. It doesn't have to be isothermal. Maybe the temperature is almost constant, or maybe, it's not perfectly reversible, but it's not exactly a constant pressure either. There's all kinds of things that can happen, but in PChem, we only want to change a few things at a time. We can't throw in realistic situations where we don't have it reversible exactly, or constant pressure exactly, or even constant temperature exactly. So today we did the isothermal expansion, we did it reversible, we did a constant pressure. Some other day, right, later, we're going to do an adiabatic expansion, and that's where Q is equal to 0. And we're going to do reversible, and we're going to do isothermal. Oh, sorry, reversible and constant pressure. Okay, so you know, it's almost like this is baby engineering, because you know, engineers, they have to deal with real situations, and they're not going to have, you know, reversible or constant pressure necessarily. I mean, they're going to have situations that are very in between. But in PChem, we deal with idealized situations, not really real situations, but of course there are real situations, and they would end up with solutions that are sort of in between. But we don't learn about that, right? We just stick to our idealized situations because we're beginners, and we'll worry about the rest of it when we worry about it. Okay, so I just want to show you, let's see, where is it? The next thing is this special problem I'd like you to do. Do we have a quiz that's due on Wednesday? Is that true? All right, so I'll wait a little longer for this. But you've had forever to do that. I would like you to do it by Wednesday, but I'll take it late. Because I want to talk about some of the results here on Wednesday. So we already did, so notice some of these things are familiar. We have an ideal gas is expanding from an initial pressure of 10 atmospheres to a final of 2.5. We have it doing this. So number 2, we did this already. That was the example I gave you at the beginning of class. I would like you to calculate the reversible way, okay? And I've given you the formula, so it's really a pretty simple calculation. This one is a little bit different, because this one, instead of, see, this is like an in-between, except each step is a constant pressure. So instead of taking off sand grains, it takes off a big chunk at a time of the external pressure. So you can see that this is sort of an intermediate case. And then I want you to also illustrate the work done graphically. So I want you to draw graphs and make them look, you know, kind of scale. You know, I don't want you, don't do them on Excel, but you know, kind of make the volumes be reasonable on your x-axis. Don't make some kind of crazy scale that doesn't make sense. Just sketch them though. You don't have to do them prettily or anything, but just make them more, calculate the initial and final volumes, which you already did, as well as the intermediate, so I also want you to calculate the intermediate volume. So when you draw your graph, it looks like it makes sense. And this is telling you that delta U is 0, and so that you could calculate Q. But that's really very simple, because it's just the negative of the work that we figured out today. So I don't, you know, maybe these illustrations, maybe, you know, that might take you a little longer. But you should at least do, make sure you have one in, you know, at least one done by the time you come to class on Wednesday, so that I can talk about, you know, just show you what those results are. Yeah. All right. All right, that's enough for today. We have, some of us will be in lab. Who's coming to lab tonight? Corey and Israel. Okay. All right. And I did post the data that you should use for working on that CHIMO lab. I even posted that for the in-person students, because everyone's doing that lab as a dry lab. And everyone got the email I sent this weekend and the corrected stuff? Okay. If anyone had any questions about that, you can hang out. I'll talk to you after if anything wasn't clear. But otherwise, I'm going to say goodbye, and I'll see a couple of you later. Okay.
Thank you, Dr. Cooley.
Yeah. Bye. Stop recording.